Risc-V instructions using a high-level language. Today we're going to resume the work that we stopped last time. We're going to try to get as many instructions implemented as we can, and in doing so we'll discuss various issues that appear when you are developing software. And one of those issues is bugs, which we inadvertently introduced last time without thinking of it. And the reason why this happened is because we had no tests to verify that our code is actually doing what we expect it to do. So let's try to trigger this bug by adding a new unit test. We'll take the existing unit test for add-I and we'll create a copy of it where we specialize it to subtract minus or add-I with -2. Now recall that the add-I instruction takes two input parameters. The first one is a register number, in this case register 0, which as we all know is hardwired to the value 0, so this results at 0. And then the second input parameter to the instruction is an immediate value, which is a signed number, in this case -2. And then we add those two numbers together. 0 plus -2 is -2. And we store the result in register 2. So our expectation is that after we run this code, the register values should be -2 in register 2. Also, while we're at it, let's get rid of these annoying warnings. All right, warnings are gone. Now let's try running our new unit test. And it fails. We get 0 back, which is, of course, quite unexpected. And I guess we'll have to figure out why that is. And a good way to determine these things is to put a breakpoint in some likely location. So let's take a look at our assembler. Maybe the assembler is incorrectly generating the wrong code for add-I. So we'll put a breakpoint here. And let's run the test inside the debugger. Alright, so let's step into this function, and as we can see, this instruction ends up with the hexadecimal pattern FFE. Let's change. Let's add another wash. All right. So here we can see that the resulting word, machine instruction word, from the assembling of an I-type instruction has in its highest bits a bunch of 1s, which correspond to the -2 that we're encoding in this instruction. Great. So then when we write that to memory, we expect that the highest significant byte should be all 1s, or FF. But when we execute this statement, B3 turns out to be 0. Which is incorrect. That's not the value that we wanted. And the problem is because we are using division when we in fact want to be using right shifts. So the purpose of this function is to take this 32-bit value and rip it apart into bytes, and then write those bytes in the order in memory that is called little endian. So what we want to do is take the the least significant bits of the word, which we're storing in the variable b0, and store b0 first. Then b1 is going to be the remainder, or the higher bits. So these instructions work correctly when value is a positive number, but when it's a negative number, we run into this bugs. So let's change all of these divisions to right shifts. So this is a right shift by 8, and then this is a right shift by 16, and this is a right shift by 32, or 24. So once that is done, if we now run our unit test again, hopefully the error has been taken care of. Indeed. So now we get a green bar. Fantastic. So we've fixed the bug, but now we need to add more instructions to make our emulator capable. Let's look at what we have. We have only one instruction, add I, but we want to add support for the add instruction, which is similar to the add I instruction, except that the add instruction takes 3 registers. So in order to test this properly, we need to set up a bunch of registers with values before we actually execute the code. So what we'll do in our run test function for add is we'll set up the emulator registers so that register 4 has the value, well, why not 4? Emulator registers 5 has the value 5, and the emulator registers 6 has the value 6. And then what we'll do is we'll store in register 4 the result of taking the contents of register 5 and adding it to register 6. So at the end of this execution, register 4 should contain the value that is stored in register 5, which happens to be 5, and the value that's stored in register 6, which is 6. So 5 plus 6 is 11. That should be the result. So now let's try running this test, and we'll quickly notice that that will not work because we haven't implemented the framework. Oh, sorry, add. We haven't implemented the framework for the support for neither assembling the add instruction nor the emulation of that same instruction. So if I now try to run this, I should get a screaming red blob. And the complaint is we don't know what this instruction is. Great. So another thing that I wanted to do is take a closer look at the mnemonics class which we have here, and if you are familiar with the C# language, we're doing something that the language does much better, which is to represent an enumerated type. So here we have an enumerated type, except we wrote it in a static class and we're using constant values. And the drawback of doing this is that these numbers 3, 4, etc. Are not very helpful when you're doing debugging. But if you tell the compiler that this is an enum, then the compiler and the runtime will helpfully display values of this type as their string representation instead of just a number. So this will help us immensely when debugging. So let's go ahead and fix this by replacing the word public const int with 4 spaces. And then let's replace all the semicolons with a comma. And then let's undo that for the namespace. So now we have an enum. Let's try building. Make sure that we didn't break anything by doing this. And I'm not sure what's going on here, but struggle a bit with Visual Studio Code. It's not behaving as smoothly as Visual Studio usually does. I'm getting used to it. I am working on becoming better on Visual Studio Code. That's just why I'm doing a lot of this work with it, but it is a little frustrating sometimes when it fails. Alright, so here we have a syntax or a type error. Operations are no longer a integer, they are now a strongly typed enumerated type. So that's good. And then here we have another, yeah, it's a little, yeah, there's something going on with Visual Studio Code. It's not really updating correctly after building. Okay, so we made ourselves an enum, but now we need to add support for both assembling, add, and also emulating it. And as I was looking at this project, I noticed that, wait a minute, we are taking the assembler to be perfect. There are no tests verifying that it actually is doing what it's supposed to be doing. So we ought to add some unit tests for the assembler as well. So let's go ahead and do that. We'll add assembler tests. Let's see, yes. And this will be in the namespace rvfun.unittests. Let's make this a test fixture and is assembler tests. Okay, so what should an assembler test look like? Well, let's add one for the add instruction that we're about to implement. So what we want to do is say Risc-V assembler, and then the test is for the add instruction. So in order to test this, we need an assembler, and the assembler requires a memory. Okay, so in order to do that, we'll say var memory equals new memory, and the memory in turn requires a pile of bytes, and we'll allocate a kilobyte like before. So there we have our assembler, and then we're going to do the assembly. So we'll say assembler asm, and then we'll say mnemonics.add, and then the destination, let's use a bit pattern that is 5 bits long. So for instance 17, that's 5 bits long, and then 21 is 5 bits long, and 31. Okay, great. So if that assembles correctly, then we should be able to read out of our memory the word that just got assembled at address 0. So let's read it out and store it in uinster, and we'll call read little endian word 32 at address 0. So that should give us back the word that we just wrote, and then we're going to compare this expected number, and we'll have to come up with what that is with what we actually read. So now let's hit the manual and find out what an add instruction should look like. So let's see, it's over here. I will know that the high 7 bits are supposed to be all zeros. So 1, 2, 3, 4, 5, 6, 7. And then the next is the second input register, RS2. And that's going to be this number here, 31, which is all ones, 1, 2, 3, 4, 5. And then RS1 is the first input register, which is 21, which is 16 plus 4 plus 1. And then we have 3 zeros for the 3-bit function. Then we have the destination register, which is the 17, 10001. And finally, the major opcode, which is this bit, these bits here. So this is our expectation, that when this is executed, the instruction that gets generated is this bit pattern here. So let's get rid of these warnings again. Let's copy the pragma from the emulator tests. Put it back in here. All right, so let's run the unit tests and see what happens. Here's our new assembler test. And it fails. And it fails because it doesn't know the operation. And notice now how instead of a number here, we get the actual mnemonic that is missing, add. Okay, great. So let's implement this instruction then. And we'll add a case to our switch statement. And here we are now dealing with a new instruction type. Recall that previously we had implemented an I-type instruction, but this time we're implementing an R-type instruction because this instruction takes 3 register operands, one for the destination, one for this one source, and one for the other source. And then the remaining bits of the instruction are used for selecting a particular function. So we need to create a function that takes the major opcode, it takes the function 3 and the function 7 fields, as well as the 3 register specifier fields. So let's go ahead and implement that. We'll call it from here. We'll say as an R, and then we need the opcode for add, which is those 5 bits. And then the minor opcode is 3 zeros, and the major opcode, sorry, the 3-bit function is 3 zeros, and the 7-bit function is also 0. So 0, 0, and then we'll pass in the remaining arguments like this. Okay. So now we need to implement that. So what we can do is we can steal this declaration and add one extra field, which is the func7 bit field, like so. And we do something very similar. We very carefully will copy this. And we missed the first line. All right, there. So first thing we do is we take the opcode, which is already located in the least significant position, so we don't need to shift it. Then we take the function 3 and we shift it up to position 12, as we can see here. And then we also want to take the function 7 and shift it to its position. And the function 7 position is bit position 25. So we'll take the function 7 and shift it by 27 bits. So now that's properly aligned. And the remaining 3 arguments, well, the destination and source 1 are correct, but source 2 is no longer an immediate, is now a register value, so we have to mask it down to force it to be in the range between 0 and 31. But the bit position should still be 20. So let's take a look at where add is. rs2 is in bit position 20. Very good. Okay. So let's call this as an R then, for an R-type instruction. Why don't we write a little comment here as well? We'll write the comment stating assemble like so, and then similarly for ASMR, just to make our intent a little bit more clear here. Fantastic. So now let's see if that passes the test. And indeed it does. Great. So now that we can assemble the add instruction, let's go over to our emulator and see whether we can cope. And we already know that we're not coping with this add instruction, so we have to add a handler for it. So let's hop over to the emulator and add a handler for add. So here's the exec function, and recall that the first thing we do when emulating these instructions is we extract the major opcode, which we created a bit field for, and we are already looking for this bit pattern, which is shared by all the instructions that take immediate arguments, but this is not a function with an immediate argument. So we need to add a case for the add major opcode, which is this bit pattern here. And so we'll take that bit pattern and add the case for it. All right. So the next thing we need to do now is, again, grab the 3 bits for funct3, these 3. So we'll have to do the same thing for this function. And then we need to create or do a switch based on those 3 bits. And now we need to add yet another level, because we have these 7 funct7 bits that we have to check. So we'll do a funct7 equals bf funct7 extract unsigned. And those bit fields and this variable do not exist yet, so we'll create them. And the bit field for funct7 is at position 25. Okay. So that will extract the high part of the instruction and put it in the variable funct7. So then we do another switch on funct7. And in the case where it is a 0, then it's an add. Look at that. Great. So in that case, we have to emulate an addition. And we already wrote the code for that. It's down here. Let's take it out of this old commented out code and paste it back in here. So we know that this is an add. So what we'll do then is take the destination register and add source 1 and source 2. But we need to actually fetch those values from the instruction. We haven't done that yet, so we will add similar code to what is happening over here. In fact, let's promote these fields up here. And then what we'll do is grab source 1 and destination. And let's put that over here. But then we need to change this because we want to read source 2, not an immediate field. So we'll need to create another bit field for source 2. And the bit field for source 2 is the one that starts at this column, which is bit position 20. Okay. And it's also 5 bits wide. So now we have a bit field for SR or source 2. Okay, and we need a variable to keep the value that we extract from the word. And that's not a signed number, it's an unsigned number. Great. So once we have that extracted, we now go to the register bank for source 1, fetch the value, go to register bank, look up register source 2 and get its value, add them together, and then put the result back in X. So this looks correct. Then we'll add a few exceptions here for the unimplemented cases. So if we'll change that to funct7, and then we'll put another default here. Actually, we don't have a... Oh, hold on. We have to say case 0 here. And we have to move funct7 out. We'll put it here. Okay. Let's reformat this file a little bit to clean it up. So if we got a funct3 of 0, then we need to read a funct, well, we use the funct7, and if that is also a 0, then it's an add. Otherwise, we fail, and then we can take this and put it over here, and then we are done with the funct3 for this case. There we go. Okay, so we're good to go, I think. No, we have an error. We forgot to pipe break. There we go. So let's build this, and then we'll try running our unit tests to make sure that that new case is running. Lovely. So now we have 2 working instructions. Not only can we assemble the add instruction, we can also emulate it correctly. And so now we end up adding a whole sequence of these instructions. So let's bring back the factorial function and see if we can get it to work. So we'll have to go to the older version of this project because I foolishly discarded the previous, or the output of the previous episode. So let's go here and see if we can find the factorial. Here's our factorial function. So we'll grab this and we'll put the instructions inside of our assembler because we want to be able to assemble these instructions. And we'll put them in the emulator as well. And we'll pick them off one by one. And this was the wrong file. I want them in the unit tests. All right. So we've already done add immediate, so we can remove those. And then multiply should be very simple. It should be very similar to add. So let's look up the definition of multiply. And it is right here. So let's implement that then. So we can take the existing. Well, we're going to make a very similar function for multiply. So why don't we refactor this function so that the pieces that are specific to add are done, and then all the other code is boilerplate, and we can put it in a separate function. So we'll call that function run test. Let's make it a private function. And what it will do is it will take as its input the expected instruction. And then we'll create just like before, a function pointer or a delegate that will, given an assembler, create the test. So what we do then is we take the body of this function, we paste it in here, we'll replace this with uinster expected, and then this is what we use the test builder for. So we'll say test builder, passing it the assembler like that. So now we will create all the scaffolding, run our test builder, which runs the assembler for us, and then we verify that the result was the one we expected. Great. So now we can just remove all this code and replace it with run test, which when given the assembler for add, it generates that word. And this is a delegate, so we'll give it a lambda like this. Nice. All right, so this should do multiplication. So now we need to, multiply. So let's run this for fun, and of course this should fail. And while that is compiling, it's already done, and it complains that there's no instruction mul. Of course there isn't, we haven't implemented it yet, so let's go to the assembler now and find the big switch statement for mul. Now mul is another ASM-R instruction, 0b, but its major opcode is different. It's this value. I think it's different. In any case, we'll use the manual as our source of truth. And then the funct3 is 3 zeros. But then the funct7 is this number. And then dest source 1, source 2, break. So there's our multiply function. And that should work. But we have to make sure that we expect the correct value also. So we can't just take the value for add. We have to use a 1 bit here, and then this bit pattern I think remained the same. So let's see if that is the case. Nope, it's not the case. Also, why don't we format these as bit patterns so that we can compare them. So we'll do this. We'll do a little trick. We'll say if uinster expected is not equal to uinster, then we will we'll call a function called toBinary, which we'll write that generates the binary representation in a field of a certain number of bits. So private string to binary. We'll pass in the uint that we want to format, and bit size, and then what we'll do is we'll make it static, and we'll close that. So what it will do is it will take the value and convert that to a string using base 2, and then we're going to pad that to the left by bit size, and then the padding value is a 0. Great, and then we return that. Alright, so now let's run our test again, and let's see why it's not happy. Okay, so it looks like we missed a 1. So let's go back to our assembler and take a look. So how many zeros do we have here? So this is correct. Maybe the shift amount is not correct. It is incorrect. It's 27 when it should be 25. So let's fix that. And the reason why we didn't see this before is because the constant for the funct7 constant for add is all zeros, so there was no way of seeing it. Great. So now we have the multiply instruction assembling. Let's go now to the emulator and let's emulate it. So we'll take our add test case, but we'll change it to multiply. And so now we'll take 4, 5, and 6 again, and instead of adding, we'll multiply them. So multiplying the contents of register 5, which is 5, with the contents of register 6, which contains a 6. 5 times 6 is 30, and then we'll put that in register 4. So now our expectation is that that register will have this value of 30, but of course we haven't implemented that yet, so if I run all of these tests, we'll get a failure. And it says, I don't know what this funct7.1 is, so we'll have to implement funct7.1. And in that case, we want to do a multiply now. So we'll take the destination equals x.source1 plus x source2. Oh, not plus, times. There we go. And then break. Fantastic. We have now hopefully a working implementation of multiply in our emulator. Well, that was nice. Good. Let's move on to the next instruction in our assembler. So let's do this SGTI thing. So it turns out that SGTI was one of these instructions that we were using in our previous, one of the first sessions, but it turns out I think that there isn't actually an SGTI instruction in the instruction set for Risc-V. There are similar instructions, so let's find the setter functions. Here they are. So if you look, you'll notice that there's this function called SLTI, which sets a bit if something is less than an integer. And that's not what we want. What we want is greater than. Well, it turns out that less than and greater than are related. all we have to do is switch the order of rs1 and r and the immediate value, but the instruction does not permit this. So what do? Well, we have to invert the logic of the following branch. What we want to do is say set if less than, and then in the following instruction we change the sense from check if it's 0 to check if it's not 0 to check if it is 0. So we'll implement slti, and then we'll implement branch equal. So let's go ahead and do that. We'll add another unit test for, hold on a second, what happened to our multiply? Oh, this is silly. Oh, okay. My bad. I destroyed the unit test for add in order to create multiply. Well, I guess we'll have to live with that. We'll create a new one for slti though. So slti is not an opcode that we have yet, or mnemonic that we have yet. We'll create it, and then slti will have the same arguments. Actually, it's an I-type instruction, so it will have maybe a longer instruction. In fact, let's give it a -2, like before, to catch any potential problems with long bit patterns. So the new bit pattern is then going to be 2, 3, 4, 5, 6, 7. And then this lowest bit will be a 0. And if we look at the instruction for slti, we'll see that the low part is this bit pattern here. And then the func3 part is 0, 1, 0. So that should be the test for slti. Let's run it. And this should fail. And then we'll go to the assembler function and add support for slti. And there's our exception, unknown instruction slti. So adding support is pretty trivial now that we have the asmi instruction, so we'll just use that, asmi. And then the bit pattern for the major opcode is this bit pattern, and the func3 is 0, 1, 0. And then we do dest source 1, source 2 as before. Nice. So the next thing that we want to do is make sure that that passes. And it does. And now we need to create a test for this instruction. So let's go to the emulator tests, and we'll create a test for slti. So let's go to the definition of slti for an explanation of what this instruction actually does. So slti places the value 1 in the register destination if the register S1 is less than the signed extended immediate when both are treated as signed numbers. Okay, great. So what we'll do is we'll write an instruction slti which will set register 4 to the value 1 if the value in register 5 is less than the immediate value of 6. So in this case, because 5, the contents of register 5, which is 5. Since 5 is less than 6, we expect the value 1 to be stored in register 4. And we should probably write another unit test for the false case. So if we compare the register 5 to the value 5, then it's not going to be less than 5. So that means that we should get a 0 in register 4. All right. Let's run all of our unit tests, and while that is all compiling and running, we will go to our emulator and implement SLTI. So the complaint here is it doesn't know funct3010. So this is line 91. So what we need to do is add funct3 here. And this is SLTI. And we're going to be duplicating the same work. So let's move these outside of the switch statement. Put them here. And in this case, we'll get the value out of the first source register, and then we're going to compare it if it's less than the immediate value. Remember, this is less than the immediate value. We check for less than-ness, and if that result is less than, then we want to return a 0, otherwise a 1, or otherwise a 0, and then we store that in the destination register. Like this. And then we do a break. Okay, let's see if that works. And look at that, it all works. Fantastic. So, we have now reached a point where an hour has passed, and we're going to reach, we've reached the more difficult instructions to assemble for Risc-V. So I am going to pause here, but next time we'll be looking at the functions that I've called goto and b and z, which actually are called something else in Risc-V. But because they are more complex than the simple instructions that we've been dealing with so far, I want to spend some more time working on those in detail. So until next time, have a good one, and hope to see you again.